In the last lecture, we have defined norm on a linear space. Norm is nothing but a function from a linear space X to the set of real numbers, satisfying some properties. Since function is from linear space to the set of real numbers, so norm associates each vector a real number. And in this way, we can see that norm on a linear space generalizes the elementary concept of the length of a vector. क्यों? क्योंकि आप लोग जानते हैं कि किसी भी वेक्टर की लेंथ मैग्नीट्यूड जो है वो रियल नंबर होता है, और यहाँ पे हम हर वेक्टर के लिए एक रियल नंबर एसोसिएट कर रहे हैं, और इस तरह से आप कह सकते हैं कि हमने वेक्टर की लेंथ का जो कॉन्सेप्ट है उसको यहाँ पर नॉर्म की हेल्प से जो है वो जनरलाइज किया है। तो हम लोग ये देखते हैं कि जो नॉर्म है उसकी हेल्प से हम लोग एक मीट्रिक भी डिफ़ाइन कर सकते हैं लीनियर स्पेस पे, और इस तरह से हम लोग ऑब्ज़र्व करते हैं कि नॉन लीनियर स्पेसेस एंजॉय लीनियर प्रॉपर्टीज़ एज वेल एज मीट्रिक प्रॉपर्टीज़। आप सभी लोग जानते हैं कि कोई भी मीट्रिक स्पेस जो है वो एक टोपोलॉजिकल स्पेस होता है, और इस तरह से हम लोग कह सकते हैं कि हमने एक रिलेशनशिप जो है इस्टेब्लिश की है बिटवीन algebraic and topological structures on X. Now we shall show that the induced metric D on linear space X satisfies the following properties. The first property is D of X comma Y is equal to D of X minus Y comma vector 0 for every X comma Y in capital X. Let us prove this result. D of X comma Y is equal to norm of X minus Y by definition of D, and this can be written as norm of X minus Y minus 0 vector, and by definition of D this can be written as D of X minus Y comma 0 vector. Second property is D of alpha X comma 0 vector is equal to mod of alpha into D of X comma 0 vector for every alpha in K and for every X in capital X. Let us prove this result. D of alpha X comma 0 vector is equal to norm of alpha X minus 0 vector, and this is equal to norm of alpha X, and by property of norm we can write it as mod of alpha into norm of X, and this can be written as mod of alpha into norm of X minus 0 vector, and then by definition of D we can write mod of alpha into D of X comma 0 vector. Now we as we have proved that any linear space is a metric space, so all the concept which we have learned in metric spaces can be used here. So we can define open sphere, closed sphere, convergence of any sequence, Cauchy sequence. So let us define open sphere in a non-linear space. In a non-linear space X, for any positive real number R, the set containing all those x's such that norm of X minus X naught is strictly less than R is called an open sphere with center X naught and radius R, because in a metric space in place of norm of X minus X naught we write D of X comma X naught, and since by definition of D, D of X comma X naught is equal to norm of X minus X naught, so here we can define an open sphere in a nonlinear space in this way. Similarly, we can define a closed sphere as the set of all those x such that norm of X minus X naught is less than or equal to R, and this is a closed sphere with center X naught and radius R. and we use similar notations for open sphere and closed sphere. Open sphere is denoted by S of small bracket x naught comma r, and closed sphere is denoted by S of close square bracket x naught comma r, where x naught is center and radius is r. Now we note that in a non-linear space, open sphere with center x naught and radius r can be expressed in terms of open sphere with center 0 vector. That is, S of x naught comma r is equal to x naught plus open sphere with center 0 vector and radius r. Let us prove this first result. S of x naught comma r is by definition set of all those x for which norm of x minus x naught is strictly less than r. And since x and x naught are elements of x, capital X, so x minus x naught is some element of x. If we denote x minus x naught by y, then here we can write set of all elements x naught plus y, where y belongs to capital X and norm of y is strictly less than r. Since we are adding x naught to each vector of x with norm of y less than r, so we can write here x naught plus set of all those y's in x for which norm of y minus 0 vector is strictly less than r. And by definition of open sphere, we can write it as x naught plus open sphere with center 0 vector and radius r. Thus, an open sphere centered at any point in x is translate of an open sphere at center 0 vector with the same radius. Now, we prove the next second result, that is an open sphere with a radius r can be expressed in terms of an open sphere with radius unity. Let us prove this result. Open sphere with center 0 vector and radius r is by definition set of all x such that norm of x minus 0 vector is strictly less than r. Then we can write, since r is a positive real number, so we can divide this expression by r, and we can write set of all those x such that norm of x divided by r is strictly less than 1. And since r is a positive real number, so this expression can be written as norm of x by r strictly less than 1. And if we write x is equal to ry, then this set can be written as the set of ry's in capital X such that norm of y is strictly less than 1. And since here we are multiplying vector y by r with norm of y is strictly less than 1, so we can write r into set of all y's in x such that norm of y is strictly less than 1. And then this can be written as r times set of all y's in x such that norm of y minus 0 vector is strictly less than 1. And by definition of open sphere in a non-linear space, we can write as r times open sphere with center 0 and radius 1. So, from these two results, we can say that if we want to use any open sphere in a non-linear space, then we can use an open sphere with center 0 and radius 1. Now, we define Cauchy sequence in a non-linear space. A sequence xn in a non-linear space X is called a Cauchy sequence if and only for given epsilon greater than 0 there exists n naught, a natural number such that norm of xn minus xm is strictly less than epsilon for all n greater than or equal to n naught and for all m greater than or equal to n naught. As we know that in a metric space, sequence xn is said to be a Cauchy sequence if for given epsilon greater than 0 there exists n naught in capital N such that d of xn comma xm is strictly less than epsilon. And in a non-linear space, d of xn comma xm is nothing but norm of xn minus xm. So, in this way we can define a Cauchy sequence in a non-linear space. And in other words, a sequence in X is said to be Cauchy sequence if and only if norm of xn minus xm tending to 0 as m tending to infinity and n tending to infinity. Now, the next definition is a sequence xn in a non-linear space is said to converge at x belongs to capital X if and only for given epsilon greater than 0 there exists n naught in the set of natural numbers such that norm of xn minus x is strictly less than epsilon for all n greater than or equal to n naught. Because sequence xn in a metric space X is said to converge at X if for given epsilon greater than 0 there exists n naught, a natural number such that d of xn comma x is less than epsilon. So, d of xn comma x can be replaced by norm of xn minus x in a non-linear space. So, we can define the convergence of a sequence with the help of convergence in a metric space. And in other words, we can write norm of xn minus x tending to 0 as n tending to infinity. And we write it also as xn tending to x as n tending to infinity, or symbolically we write limit n tending to infinity xn is equal to x. Now, the next definition is completeness. A non-linear space X is said to be complete if and only if every Cauchy sequence in X converges to some point of X. Thank you.